Okay, welcome back to our work on the equation of state of an ideal gas. First, when we use the word state in this unit, we're talking about something different from liquid, gas, solid. Liquid, gas, solids, what are those? They're not states? No, we're going to call those phases. So what is the equation of state? It's this. We call it that. This is the ideal gas law, but we call it the equation of state because the state is simply the particular combination of pressure, volume, and temperature. These are the state variables or the state quantities which define a particular state. If you change the volume, now you have a different state. Okay. I'm going to erase what we were looking at here, and just so I have room, but you do not need to write what I'm about to put into your notes. But I do want to look at why we cannot use degrees Celsius in the equation. Let's say you have something like this, 2 times 3 over 4, and that is obviously equal to, well, instead of 2 over 4, I'm going to put 4 over 8. Right? But if I add 1 to both denominators, are the two sides equal? No, you can actually calculate. They're not equal anymore. You would have to add, 2 to make it equal. And so if you add the same amount to the bottom, this is no longer true. Let's say you take a gas and you start with a small volume, so it has some first volume, some first pressure, some first temperature, and we expand it to a larger volume. Now none of the gas leaks, so there's still as many moles. The number of particles, the number of moles inside has not changed. We just have a new volume, but because the volume changed, the pressure and temperature adjust as well. The number of moles is equal. From the ideal gas law, PV equals nRT. You can isolate N, and what does that equation give? PV over RT. So, okay, well let me just plug in P1 V1 over RT1 on the left, and PV over RT on the right using the 2 subscript. P1 V1 over T1 equals P2 V2 over R. And you guys will do problems like this, exactly like this. We will see this in the future. Well, the R's cancel out because it's the same, doesn't change. It's a constant. And look at what we have. If you try and change this from Kelvin to Celsius, degrees Celsius, you can actually end up adding 1 just like we did over here. That is almost certainly what you will be doing. Almost guaranteed. Well, not guaranteed, but in many cases that's exactly what will be happening. So you can't just add the same, you can't just convert to Celsius because you're adding a negative 273 to both sides, to the bottom denominator and the left denominator and to the right denominator. And you can't just do that because you risk changing the equality to an inequality. Okay. Now, so far, everything we've talked about, right, all of this business of the equation, this equation, PV equals nRT, that, the pressure business, everything here about these assumptions, all of it applies to this magical ideal gas, which doesn't really exist in the world. Why do we talk about ideal gases? We use them as a model. They model real gases. Model real gases. But just like every model, there are limits. Sometimes a real gas is going to be very similar to an ideal gas. Other times a real gas is going to be quite different from ideal. So when will a gas act ideal? One of the assumptions we mentioned is we said that the volume of the container here, each molecule has a negligible volume compared to the whole container. So if you add up all of those negligible volumes and you divide by the volume of the entire container, this value should be relatively low. Relatively low. The volume should be big compared to the moles, how many moles you have. In other words, the density, the molar density is low. You don't have all of these things really tightly clumped together, because then your molecules aren't really like a gas, they're more like a liquid or a solid, and the intermolecular forces are going to play a bigger role in their interactions. Okay, so you need a low density, a low molar density. N over V should be low. Let's write that down. This is not the official final answer. We're going to use this to figure out when real gases act ideal. N over V is low. Wait a second. PV equals nRT. N over V. What's N over V equal to? Rearrange this equation. Try it out. N over V is pressure over R, ideal gas constant, times the Kelvin temperature, absolute temperature. So if you want the right side to be low, pressure, should it be high or should it be low to make N over V low? Temperature, should it be high or should it be low to make the density low? The answer is a real gas will act ideal if pressure is low and temperature is high. You want a small numerator and a big denominator to make this thing, the whole thing, low. So those are the two conditions. You will see questions like this in multiple choice form. Under which of the following conditions will a real gas act ideal? Low pressure, high pressure, low temperature, high temperature, and you choose those that apply. Okay, so what if this is not satisfied? Well, if P is high, pressure is high, that means those molecules are really close together. They occupy a pretty significant volume. There's not a lot of space between them. And temperature is low, causing them to kind of, move from a gas, maybe act more like a liquid. Under these circumstances, a real gas doesn't act very ideal. And the reason why is just what we showed. PV equals nRT. If you isolate N over V, you get P over RT. So to make that go down, you need pressure to be small and temperature to be high. Okay, now skip to page 8. Skip ahead, number 8. Skip this, go to number 8. And we're going to solve this. The temperature difference between the inlet and outlet of an air-cooled engine is 30 K. Alright, let me draw my engine. There's some inlet and some outlet. Alright. I'll call this the outlet. And here's the inlet. And the idea is it's an air-cooled engine. So the engine is hot, but the air flows and that's what cools. So air flows and that's what cools the engine. The engine generates 7 kilowatts of waste power. Alright, that's power. 7.0 kilowatts. They also said the delta T, the temperature difference, is 30 K. So power, delta T, heat is being taken away by air, so the air absorbs heat. Oh, this makes sense. The air absorbs heat from the engine and then takes that heat away. So if the air is absorbing heat, I'm starting to think Q equals mc delta T, because the air heats up, taking away the heat, taking away the internal energy from the engine, and then there's some power for that wasted energy that the air absorbs. The power of the wasted energy, the power of the energy that the air has to absorb, is P equals Q over delta T. Calculate the rate of flow of air in kilograms per second needed to extract this power. Kilograms per second, wait, kilograms is mass, per second, that's time, so I'm looking for mass over delta T. That's my unknown. The specific heat capacity, look at this, they gave me C. So yeah, I know C, I know delta T, and I need M over time, mass per unit time. Well, here's mass, this is Q, here's time. Let me plug in and combine these two equations. P equals Q, which is mc delta T, over change in time. So, oh, look, m over delta T, there it is. If I isolate m over delta T, I'm not going to isolate, I'm just going to separate it off. I know the value of C. It's 1.01 times 10 to the 3. Check the units. It is my mass. My mass will be in kilograms. Good. Plug in the value of delta T, 30K. 30K is what the air has to absorb. Here's how easily here's the capacity for the air to absorb heat. And the power that it has to absorb, the power that the air has to absorb, is 7 kilowatts. 7.0 times 10 to the 3 kilowatts. So you solve for m over t. And what do you get? The flow rate in kilograms per second comes to 0.23 kilograms per second.